This is 4.1 Intro to Chemical Reactions. So today we're going to be focusing on types of reactions, and before we get into the different types of reactions, which should be review from chemistry, first we need to talk about how reactions kind of occur. Generally, when we're looking at reactions, we're looking at ions that are combining together to form a precipitate. So generally, whenever we are having a chemical reaction occur, we want our salts to be in ion form. Okay, so in order to achieve that, we need to dissociate in water our salts. Okay, so for example, if I have NaCl, okay, I can dissolve that in water or dissociate it in water in order to get my two different ions, Na and Cl. Okay. So then once they're in the ion form, then they can kind of go through these different types of reactions. So the first type of reaction is the synthesis reaction. This is just when elements or simple compounds combine to form a single, more complex compound. So the basic format for a synthesis reaction would be A plus B is going to yield AB. Okay, so for example, if I have magnesium plus oxygen, it's going to yield MgO. Okay, now just as a reminder, metals can be found on their own, but generally our non-metals are going to be diatomic, especially those gases. So make sure you're just aware of that. And then remember too, whenever we're finding the product of a reaction, we need to do the crisscross method using the charges of the two atoms. Okay, so magnesium has a charge of +2, oxygen has a charge of -2. So when I do the crisscross, that's why I get the MgO, because basically those subscripts are going to cancel out. Okay, our next type is decomposition. Okay, with this one, we have a single compound that's split into two or more elements, or simple compounds. So dissociation could be kind of associated with decomposition as well. So here, the basic formula would be AB yields A plus B. Okay, so if I have, for example, HgO, okay, I'm going to yield my mercury, which can be by itself, and then my oxygen gas as its product. Okay, our other types of reactions, which we'll spend a bit more time on later in this chapter, or in this unit, will be acid-base reactions. So with this, an acid and a base react to form water and salt. So the basic formula for acid-base reactions is we're going to have a hydrogen donor, which is our acid, plus a hydroxide donor, which acts as our base. And then they're going to combine together to form a salt plus water. Okay, so a perfect example of this is hydrochloric acid plus sodium hydroxide. Okay, and then basically this is like a double dissociation or double displacement type problem. So my hydrogen from here is going to combine with my OH here in order to form water. Okay, and then the two ions that are left over, so the sodium and the chlorine, they're going to combine to form that salt. All right, and then we have our oxidation reduction reactions, or redox for short. Okay, these result in a change of the oxidation states of participating species. So we're going to talk a lot about redox reactions. They're a bit more involved. This is a new type of reaction that we really didn't cover in basic chemistry. But basically, if I have an ion, for example, okay, and it is going to accept electrons, this is going to change its oxidation state to going from a +2 charge to a neutral charge. Okay, so we'll kind of deal more with redox a bit later in this unit. All right, our next one is hydrocarbon combustion, and this is complete combustion that we're specifically talking about here. So we're going to have some type of hydrocarbon, which is going to consist of a certain amount of carbons and a certain amount of hydrogens, plus oxygen is going to yield CO2 plus H2O. If you remember from chemistry, we also talked about incomplete combustion. With incomplete combustion, it just means that we don't have enough oxygen. So we're going to get carbon monoxide produced and then carbon as a byproduct. And with that incomplete combustion, we're going to get a lot of like black smoke, and that's where that carbon product can be seen. Okay. And then we also have our precipitation types of reactions. So double displacement, okay, also single displacement. Can form a precipitate as well. So a single displacement, we have A plus BC, okay, and so A is going to come in and bump out, like our B, for example. Okay, so that's your Mr. Steal Your Girl type of reaction. And then with our double displacement, we have basically like two couples. So like if we had AB plus CD, okay, and they're going to rearrange or switch partners. So A is now with D and C is with B. Okay, now one thing to note is that with our precipitation reactions, we can write them as net ionic equations, which is slightly new compared to what we talked about in chemistry. Okay, so when we are doing net ionic equations, we're going to take out the specter ions. So specter ions, okay, these are not involved in forming the precipitate. Okay, so these are going to remain as ions in the solution. They're not going to precipitate out. So basically, they are not involved in a chemical reaction. Because remember, we have different signs of a chemical reaction, one of them being the precipitate. So if no precipitate is formed, we're going to assume with these dissociation or displacement reactions that no reaction is formed. Okay, so if we look below, okay, at this equation, we have AgNO3, which is aqueous, meaning that it's been dissolved into an Ag ion and an NO3 ion. And then we have NaCl, also an aqueous, so this is also in its ion forms, okay, is going to yield our AgCl, okay, notice the S standing for solid. So this is our solid, and then we have NaNO3, which is also still aqueous, okay? So the thing that we need to focus on is what compound was formed. That is our precipitate, okay? And for a precipitate as well, this can be a liquid or a solid, okay? So both of those would be considered precipitates for these net ionic equations, okay? So because our solid that was formed is AgCl, we're going to go ahead and write that as our product, okay? So the only ions that we're concerned with on the reactant side are the ones that actually form this solid. So from this first salt, the AgNO3, okay, we pulled the Ag, which has a charge of +1, okay, or I guess we would just put the plus. All right, and then from our NaCl, we're just concerned about the chlorine, so we're going to get the chlorine ion from the salt, okay? So this would be our net ionic equation for this particular problem, okay? So just make a note, if all the species are spectator ions, okay, meaning that no liquid or solid was formed as the product, okay, it just means that no chemical reaction occurs, okay, which is kind of what I was explaining a bit earlier. All right, so for this one, we're going to write the net ionic equation. Again, I'm going to look at what was my precipitate that was formed. So this is my precipitate. So I'm going to go ahead and write in my product. Okay, so looking at the other side, from this salt, I got my CO3, and I'm going to do reverse crisscross to determine what the charge is. So it must have a charge of -2. So my CO3, 2 minus, plus, okay, and then from this salt, I got my magnesium. Again, when I do reverse crisscross, the 2 is going to come back up. So my magnesium is going to be +2 for the net ionic equation. All right, for this one, okay, again, I'm going to do the net ionic equation. Okay, well, looking at my product side, I'm going to look for my precipitate. In this case, it is a liquid instead of a solid. So I'm going to go ahead and write this in. Okay, and so from my other side, I'm going to determine my ions that I pull from each salt. So from this salt, I'm pulling my hydrogens. Okay, so I'm going to have my hydrogen, which is going to have a positive charge. Okay, and then from my sodium hydroxide, my NaOH, I'm going to pull my OH. Notice there's a 2 out in here. So I'm going to have 2 OH minus. Okay, and so one thing I do want to go back and do for each of these is determine what types of reactions each of them are. Okay, so if I go back to this first one, okay, this one would be double displacement. Okay, this one is also a double displacement. Okay, this one, if we look at the net ionic equation, we have a hydrogen and a hydroxide ion that are being combined, and it's going to form water. And then if we look at the total one, there is a salt over here. Okay, so this is actually an acid-base reaction. And then the last thing I want to do today is just going over balancing equations. Again, this is a review for you guys, but I did just want to do kind of a harder problem just to remind you how you can use half numbers in order to help you solve a balancing equations a bit easier than just guessing and checking. Okay, so first thing I like to do is I like to split my product and reactants into 2 different sides. Okay, and then I list my species that I have on my reactant side. So I have nitrogen, I have hydrogen, and I have oxygen. Okay, and then on the other side, I like to write them in the same order just because it's easier to not get them mixed up because we want to make sure that they match on both sides. Okay, the next step is to count how many I have on each side. So on my reactant side, I have 1 nitrogen. For hydrogen, I have 3, and oxygen, I have 2. Okay, on my product side, I have 2 nitrogen, 2 hydrogen, and 1 oxygen. All right, so I'm going to go ahead and start with my nitrogen. Okay, so in order to get 2 nitrogens on my reactant side, I need a 2 out in front of my NH3. So that's going to change my nitrogen to 2. So now they match, but it also is going to change my hydrogen to 6. Okay, so now my nitrogens match on both sides, but my hydrogens do not. So let's go ahead and take care of that. So on my product side, I need to get my hydrogen to 6. So I'm going to have a 3 out in front of my water molecule. Okay, so now I have still only 2 nitrogens on this side. My hydrogen is now at 6. Okay, and my oxygen is at 3. Okay, so this is where we kind of run into a problem here, okay, because I have 2 oxygens on my reactant side and I have 3 on my product side, okay. So one thing that I can do is determine what can I multiply this oxygen by, okay, this basically the subscript of 2 in order to get 3. Okay, so I can multiply it by 1.5, okay, and that would give me 3. Okay, so now it is balanced, okay, but recall we can't have a decimal, okay, or a half molecule basically of oxygen. So then once we get it balanced, and if you have a half number, what you can do is you can just multiply all of these numbers out by 2 in order to get rid of that half number. So I'm going to go ahead and do that. Okay, so this is going to become a 4. This will become a 3. This will become a 2. And then this will become a 6. Okay, so now we're balanced and we don't have a half number in our equation.